You remember that from Coulomb's law, we know that a charge has a field around it that is inversely proportional to the distance from the charge, and it's basically kq over r squared. That's just the property of the charge that creates that electric field. And also, if the charge is moving, it creates another field that's a magnetic field. And magnetic field of a moving charge, suppose there's a positive charge here and it's moving at speed at velocity v, velocity vector v, and it has a charge q. It creates a magnetic field that's called V around it, and it's given by this formula, a constant mu naught over 4 pi. I will introduce the constant later. The charge q times v cross r hat divided by r squared. R is the radial vector from the charge to any point. For example, consider a coordinate system where the charge is at the origin, and then at any point in that coordinate system, which you can denote by a vector r, it has a magnetic field like this. You see, magnetic field is a constant. This is like 1 over 4 pi epsilon naught that we had, right? Or k. This is the charge q divided by r squared. But there's this also. The magnetic field depends on the speed or velocity. And this also gives you the direction. R hat is the unit vector in the direction of r. R hat is basically the vector r divided by its magnitude, r. If you divide a vector by its magnitude, it becomes a unit vector in that direction, right? So this is r hat, and this is the velocity of the charge. The charge is positive, it's moving in that direction. Of course, this formula works if the charge is negative, but for now, consider the charge as positive. At any point in here around the charge that's moving, there's a magnetic field that's given by this formula. So what direction do you think my magnetic field of this is at this point? The direction of the magnetic field given by this formula, you say mu naught q, and these are all scalars. The only vector part is this, right? What is the direction of v cross r in this case? V is this way, r is this way, r hat. V and r hat. That gives you the direction of magnetic field at this point. It's a bit more complicated than Coulomb's law. Remember, E, the electric field, is just k, or 1 over 4 pi epsilon naught, q over r squared, r hat. Right? But here, it's a bit more complicated. And because of this cross product. What is the direction of this cross product at this point? Suppose the charge is moving in the plane of the board, and this r also is in the plane. Outward, perpendicular to the board, right? But outward or inward, both of these are perpendicular to the board, right? Yes, the cross product is perpendicular to the plane passing through V and r hat, which is the board. But perpendicular to the plane of the board has a twofold ambiguity. It could be outward, it could be inward. Which one is it? You have a cross product, you put your 4 fingers in the direction of the first vector and turn into the second vector. And your thumb shows the direction. So if I put in the direction V, turn into r hat, my thumb shows the direction. So this twofold ambiguity that we have, this is removed by right-hand rule. You put the 4 fingers of your right hand in the direction of the first vector, turn into the second vector. For example, if you do it this way, you put in the first vector, you want to turn into the second vector, you can't, because your hand only goes one way, right? So you have to turn your hand this way to do that. And because the hand has this property, we can use it. Otherwise, we couldn't, right? To remove this ambiguity. Into the board, it's denoted by a cross. It's like looking at a dart from behind it. You see a cross. If the dart is coming toward you, you see the point. So if we have a notation, this means into the board. So in this case, V cross R is into the page if the charge is positive. If the charge is negative, when you find V cross R, you multiply by negative, it flips it around. All right, so if this was a negative charge, like an electron moving this way, the magnetic field would be outward, right? And now imagine R is this way at this point. Now it's not in the board. Which direction would be the magnetic field?
Downward.
Downward. V, see, if you put forefinger in the direction of V, you cannot turn this way. You have to turn your hand. Our hat is this way. So it is downward. So at this point, the field is downward. What about this point? If R is this way, our hat is this way, right? So V, again, cross R. Our hat is out, right? At this point, the field is out. At this point, it's into the page. Any point below this velocity line, the field is into the page. Any point above, the field is out of the page. So in fact, if this is the velocity vector of the particle, the field is circling around it. At any point, it is perpendicular to the radial direction this way. And also in this direction, because V and R hat will be in the same direction, you get zero B field. If you go the other direction, B and R hat are in the opposite direction, it is still zero cross product. So the field is zero in the direction of the velocity. It is zero in the other direction. It is more intense in the perpendicular direction to the velocity. It is circling around. And also it is depending on distance. The closer you are to the charge that's moving, the stronger the magnetic field. The further away is weaker magnetic field. So it not only depends on the distance, but also direction, right? And the direction of magnetic field is always perpendicular to the velocity and circling around the velocity vector. So it is a lot different from this. This is only in the radial direction in all directions. If the charge is positive, the electric field is going away from it, pointing away from it. And if it is negative, it's pointing toward it. And it is just further you get, it's weaker, closer you get stronger. It's easy to understand. But this one is more involved. It's circulating around the velocity vector, stronger in the perpendicular direction, weaker in the forward or backward direction. And then, if you have a piece of wire, like the small DL, that has current I in it, current is Q over T, right? Charge over time. If you have current, it means that there's charges moving in that direction. It's the same as this one. So it turns out that instead of QT, you can use I times L, or I times DL. Why is that? Because I is delta Q over delta T, right? So suppose that there's a charge from here moving to this point, delta Q, and it takes delta T to do that. If you want to write this, Q will be like delta Q, and then V will be delta L over delta T cross R hat. This is Q cross V, right? Q cross V becomes delta Q, and V becomes delta L over delta T, right? And cross R hat. And now you consider this delta Q over delta T separately. So you get equal to I delta L cross r hat. So for a small piece of wire that has current I in it, with length delta L or dl, we can say the magnetic field created, B, created by that is mu naught over 4 pi I dl cross r hat divided by r squared. And because this is a small piece, we call this also dB. Because small piece of wire, B is created by a whole wire. For a small piece, we call it dB. And this is called by Biotavart Law. That gives the magnetic field of a small piece of wire that has current I in it and at distance r. And now we still need to see what this mu naught is. And mu naught is a constant, is like epsilon naught in electricity. It is by itself 4 pi times 10 to the negative 7th. And the unit of that, because the unit of B is Tesla, becomes Tesla meter over amp, is the unit of mu naught. And this mu naught over 4 pi cancels, is just 10 to negative 7. This is called permeability of free space. It's another property of vacuum. These are two important constants, epsilon naught and mu naught, in electricity and magnetism. And they are working similarly to each other. Everywhere you have in electricity, you have epsilon naught. Instead of that, in magnetism, put 1 over mu naught. It works the same way. Remember in the Coulomb's law, this becomes 1 over 4 pi epsilon naught, right? In here, it becomes mu naught over 4 pi. If we have a B field, like in one direction, let's say it's created by some moving charges or currents, and there's a charge that is moving in this magnetic field. Let's say this is a positive charge, this positive Q, and it's moving in with this velocity v. It has force acting on it. The force, magnetic force, Fv, has a magnitude and direction, and it can be expressed as Q times V cross B. This is the magnetic force, and you know how to do the cross product. At this point, the B field is this way, parallel to the magnetic field lines. This is B, so this is B vector at this point. And the angle between them is, between velocity vector and B vector, is phi. And then, in order to find the cross product, do V cross B, 4 fingers in the direction of the first vector, times in the second vector. You get a vector that is now going into the page. So the force on this, if you want to show it here, it will be with a cross. It's going into the field, into the page. Now, there are a lot of applications of this. For example, the first time they realized that electric current was made of moving negative charges rather than positive charges, because electricity was set up before they realized that there are electrons that are moving. They thought that there are positive charges that are moving in the direction of the current. This was unknown until somebody named Hall designed an experiment. The experiment was like this. If you have a belt of wire, a belt-shaped wire, means it is a flat belt. It has a thickness very thin, but it's very wide. And it's made of copper. And you send current through this. And then you put magnetic field on this. like magnetic field, let's say, is going into the page. And then there's a current this way. So we can set the current, we can put the battery, the positive side of the battery is here, the negative side is here. So let's say it's connected to a battery like that. Negative, positive. So that the current is going up. This is the current. Right? So this side is positive, this side is negative. And this wire, which is like a flat belt or strip, is inside this magnetic field. And now, what happens if the charges that are moving and creating the current are positive charges? So if there are positive charges that are moving in the direction of the current, what would be the force acting on them? Can you figure out which direction is the force on these charged particles? The field is into the page, so V is up in direction of current, so V cross B is which way? It will be this way, right? The force of the positive charges will be this way, right? You get lack of positive charges here and accumulation of positive charges this side. And then if you find the potential difference, like let's say you connect this to a galvanometer, you can see that this side is positive, right? And this side is negative, meaning that there will be current going this way. You get this side positive, this side negative, if the positive charges are moving and creating the current. But there could be negative charges moving. What if negative charges are moving? If the negative charges are moving, like electrons, to create this current, the negative charges have to move in the opposite direction. So the negative charges move in this direction. And now what is the force on the negative charges? Can you tell me which direction is the force on negative charges? If the negative charges are moving to create this current, they have to move downward, right? And which direction is the force? V is downward, right? B is into the page, so they're like that. V cross B is that way, but because they're negative, the force is this way. So the force will be the same way, both for positive or negative charges. So if the positive charges are moving, creating the current, this side will become positive, and this side becomes negative. But if the negative charges are moving, this side becomes negative, this side becomes positive. By deciding which side is positive, which side is negative, I mean by measuring, you can determine whether it's the positive charges moving or negative charges moving. And when this experiment was done, it was determined that this side is negative, this side is positive. So that means that there are actually negative charges that are moving and creating the current. And those we know now that are electrons. And this is called Hall effect. And this experiment was done by some person named Hall. So this is Hall effect and Hall experiment. Then we understood that the negative charges are moving and creating currents. So now, if they knew that from before, they would name the charge of electron positive, the charge of positron negative, so everything would be working out. But because this historically was the other way around, they're stuck with, the negative charges are moving in the opposite direction of the current and creating the current, which is a little bit awkward to say. Anyway, this was one of the applications of that. Another application of this is you can make a velocity selector using this. If you have a cross field, let's say you have an electric field this way and magnetic field perpendicular to that. Let's say magnetic field is that way. So this is electric field that is this way. And magnetic field is perpendicular to that into the page. So we have both electric field and magnetic field. Charge particle, let's say positive charge particle, is moving in this direction. How many forces are acting on this charge particle? If you ignore force of gravity, which is usually much smaller than electromagnetic force. Two. Which ones are those?
The magnetic and the electric.
Magnetic force and electric force. Which direction is the electric force? In the direction of electric field, right? Because it's positive in that direction. So there's a force here, this force of electric field, we call it. And which direction is the magnetic force? This way, right? So the magnetic force is this way, FB. And what is the electric force magnitude? If the charge is Q, let's say, what is the electric force? So force of the electric field is equal to, the magnitude is Q times E, right? And the force of the magnetic field is Q times V times B times sine of the angle between them, because V is perpendicular to B, the sine of angle between V and B is 1. So it will be QVB, right? So FB will be QVB. If the velocity is in a way that these two balance each other, if you put these into equal to each other, FE equal to FB, then QE equals to QVB, right? And then Q cancels out. E should be equal to V times B. So V is E divided by B. If the particle is moving with this speed, then the forces balance on each other, so it will go right through. But if it is going at a smaller speed, what happens? Then the magnetic force is smaller than the electric force. So what happens to this? There's a net force this way, the particle will go this way, right? And if the speed is more than that, more than this value, then the force of magnetic field is bigger. Then there's a net force this way, so the particle goes this way. So if you have a tube here and send the particles through it in this perpendicular to both of these fields, it only lets the particles that have certain speed passing through. The particles that don't have that speed, they get deviated and hit the sides of this tube, and they don't go through. So the particles that are going in that direction, they have all the same speed if the tube is long enough and thin enough. This is called velocity selector. It selects a certain velocity. That is very important in some experiments. For example, when they do mass spectroscopy, they use this velocity selector for that experiment. Before we get into that mass spectroscopy, let's do another thing. If you have a magnetic field, let's say magnetic field is going into the page again. You have a positive charge particle moving with velocity v. We want to see what is the path of this particle. What do you think? When it goes like that, this velocity at this moment is like this. What is the force direction? The force direction will be to the left, right? This is force. And then what happens when the force applies this way? The particle deviates, right? Later on, the velocity will be a little bit this way. Will the force stay the same direction? Force is always perpendicular to velocity and the magnetic field. So as the velocity turns, the force also turns, right? And it goes like this, right? So what kind of path do you think it takes? It's because the force and acceleration is always perpendicular to velocity. The path has to be circular. In a circle, you have velocity and acceleration are exactly perpendicular, right? So it goes on a circle. And the acceleration is toward the center always. It's perpendicular to the velocity vector. We want to know the radius of this circle. This circle has a radius r, or let me call it capital R. If you have a charged particle of charge q, and it has a mass m, and it has a velocity that's perpendicular to magnetic field, what is the radius of that circle? Can you work that out? The force of the B field is equal to mass times acceleration. So that's toward the center. But force has a magnitude of Q and times V times B because V and B are perpendicular. And equals m times V squared over R. And then one of the V's cancel, so R becomes mv, which is momentum of the particle, divided by the charge, the absolute value of the charge, you may say, times b. This is the radius of the circle. Okay, so in that mass spectroscopy, they use a velocity selector here, and then when the particles come out, they send it through another region. Let's say the magnetic field is now out of the page in here. Magnetic field is out of the page, and then V is this way, V cross V is this way, so they turn around on a circle, right? And when they come on a circle, they put a detector here, the particles detect at different points in here, which is a distance from here of 2r, right? So you can determine with the detectors, you can determine how far what r is, and because V is known from the velocity selector, and B field is set up here, it's another B, and charge is known, so the only thing that is missing is this. With the finding R, you can find the masses. That's how they do mass spectroscopy. They find mass based on this R, based on this R. So this is 2R. So when they detect that, they measure the 2R, find R, and from all of these others that are known, we can find the mass. That's how they know, for example, mass of different isotopes of a certain material. Another thing is that this radius, because it is depending on V, it has a certain property. What is the period or frequency of motion on this circle? If you want to find the time period for one circular motion here, time period. What is the time period? You know time period, right? It's the time it takes for one complete term. Time period, you usually call it t, but if you look at the speed, it goes at 2 pi r divided by t. That's one complete cycle divided by the time for one cycle is the speed. And Now let's put R equal to that. If we put V equal to 2 pi over T times R, which is mv over qb. And then V cancels out. You get the time period equal to 2 pi m divided by qb, right? This is something very important. Do you see where the importance is? It doesn't depend on the speed, right? So it may seem very ordinary, okay, doesn't depend on the speed, big deal. But that gives you some clue to some smart people, the clue to make some particle accelerator. With the fact that when you are inside the conductor, the force, the electric field inside the conductor is 0. That gives you some tool to make particle accelerator. Actually, the first particle accelerators that were built was because of this property. Now I'm going to explain briefly what I mean by that. So let's say you make 2 layers of half-circle conductors. They call them Ds. So let's say it's a disk of conductor. Put 2 of them, like 2 layers of these, and cut them in half so that you have about half circles. So there are 4 Ds like this. And then you put, you make this half positive, the other half negative. I mean, you connect them with a battery, right? And then let a particle be released from positive charge, will release from here and goes to the other side. So the positive charge goes to the other side. Because of the potential difference, it gains some speed. And then put a magnetic field vertically this way. And when you put magnetic field, this particle turns around and goes this way. Okay? And then while this is going around, you change the polarity. And then now this side is positive, this side is negative. Again, the particle accelerates, gets more speed. When the speed is higher, it goes on a bigger circle. So it goes on a bigger circle like that. And then while it's doing that, you change the polarity again. Then it gets more speed, it goes on more bigger circle. While it's doing that, you change it and you get more and more and more. It goes until it gets to the edge. And the bigger you make the disk, the bigger speed you can get. And why is that important? Because you make alternating voltage with certain frequency here, because the time it goes from here to here, it doesn't change. So you can just make them alternatively, plus or minus, with an alternating current or alternating voltage, and this accelerates to the highest speed. That is called cyclotron. There are many of these cyclotron. This is called cyclotron. And each one of these are called Ds because they look like a D. And there are conductors, and they connect them with the alternating voltage and accelerates particles. every particle accelerator that you see, they are usually one of the first steps to get to the high, very, very high speed. They use one of these to increase the speed of the particle. At the beginning, you can just have two plates, and for example, send electrons from one plate to the other. It goes fast, and then that will be the starting point, and then goes faster and faster with doing this, and take the outcome of this, get it to another kind of accelerator, which is called Synchrotron. And those are the bigger accelerators. And there are many of them. Okay, so you see this property enables you to make a particle accelerator. And some other aspects of this circular motion is that when the particles that are coming from the sun, they go through the Earth atmosphere, Earth magnetic field, they turn around, and of course, if you have, instead of being perfectly perpendicular to the magnetic field, you're not perpendicular, then the perpendicular component of the velocity makes it go on a circle, so it will be perpendicular component, and it also goes with the other component of velocity. It goes like this. It goes on a helix, like a spring woven. So as the particle going around a circle, it also goes in one direction, perpendicular to that plane of the circle. And of course, this is all for uniform magnetic field. But if the magnetic field is converging, then there will be a backward force acting on the particle. So what happens in the magnetic field of the Earth, where it's stronger at the poles and weaker elsewhere, the particles spiral onto the pole and then come back, go to the other side of the Earth and come back. When they hit the particles in the atmosphere, when they're going through this kind of motion, they create an aurora, they create some light. Because the electrons or particles that are hitting the other atom send the electrons inside those atoms to the higher level, and then they relax back, give you some light. It creates some light, they call it northern light, that you can see in northern Canada, or some other parts of the world in the southern hemisphere. I think if you look at YouTube, there are lots of pictures or videos of these lights that are very fantastic and nice to look at. So that's also from this kind of motion.